All right, so today we are doing our final lesson in Unit 4, and this lesson is on the immune system. Now, during our last 3 lessons, we talked about how our body maintains itself to keep everything in proper working condition and at peak efficiency. And there are systems in place that respond to changes in the external environment and help to guard against various imbalances. But what happens when something actually enters the internal environment and throws off that balance from within? In that case, you have the immune system, which is responsible for keeping us free from disease and keeping organisms from upsetting our internal balance. And if in the case where it's not possible to keep these organisms out and they actually gain entry, then we also have mechanisms in place. Our immune system has mechanisms in place to deal with the intrusion. And then after this, once the organism that has gained entry is dealt with, then everything returns back to normal. So in today's lesson, we're going to focus on our immune system and how it prevents intrusions of various microorganisms and how it deals with intruders that actually manage to get in. So we will be focusing on some of the appropriate terminology that is related to this type of homeostasis to the immune system. We will be talking about the inflammatory response. We will learn about antigens and antibodies, anaphylaxis, and immunity. We will also evaluate some various human health conditions that arise from various human activities on the environment, and we'll also learn to describe the functioning of the immune system as it relates to the maintenance of homeostasis. And some of the questions you can keep in mind as we're talking about our lesson today is, what are the disease-causing organisms and how do they invade the body? Also, how is the body able to then fight off these disease-causing organisms? And what will happen when in the situation where the immune system does not work properly? So actually, I apologize for this interruption. Can I just put you guys on Sorry, guys. Yeah, I'm back now. All right, so am I sharing the right screen? Does everybody see this? Okay.
Yes.
Thank you so much. All right, to continue with our lesson, I apologize very much for that interruption. So where were we? Right. So our body's defenses. So throughout the day, at any given moment, our body is actually bombarded with many disease-causing organisms called pathogens that can cause us harm. And especially currently, there is actually quite a lot of those pathogens going around in the community and in the world. So for the most part, we manage to, our body manages to take care of these pathogens and keep them at bay. So we're mostly quite unaware of them. But it's only when one of these pathogens actually manages to enter our system and begin to multiply that we start to show symptoms of their entry and their attack on our bodies. Pathogens come in many forms. They can be bacteria, they can be viruses. Bacteria are those small single-celled organisms that will multiply in our tissues, whereas viruses lack that cellular machinery to replicate, so they invade our cells and literally hijack our cells and force the machinery of our cells to create and replicate more of those viral particles. Viruses are actually very specific, meaning that certain viruses will only invade certain cell types. And about 40 years ago, there was a new pathogen that came around and started to appear on the horizon, and this was called the prion. And this name is derived from its meaning. Prion stands for proteinaceous infectious particle. And prions are quite abnormal proteins that can actually influence normal proteins to take on abnormal shapes. And a good example, a best known example of prion disease is mad cow disease. And currently, there are very few defenses against prion type diseases. So our first line of defense and the single greatest defense against pathogens is our skin. It provides this tough protective barrier that usually can't be penetrated as long as it's intact, as long as you don't have any cuts or lesions or scratches. But there are certain regions on our body where you have this tough form of skin is not present. And in those areas, you need other defenses in place. One of these areas is the mucous membranes that are around the openings in our body, that those openings are vulnerable to pathogens, such as our mouth, for example, such as our nose. So in these areas, some of these membranes, especially in our mouth, have acidic type of secretions. And by maintaining an acidic environment, they really inhibit the growth of pathogens. And the mouth, as I said, and also the female reproductive tract are good examples of mucous membranes that maintain acidic secretions, and by maintaining an acidic environment, really inhibit the growth of pathogens. But also tears, saliva, mucus secretions, and sweat. All of these contain an enzyme called lysozyme, and lysozyme helps to break down bacterial cell walls. Also, the mucus secretions and the cilia. And cilia are those tiny, very fine hair-like protrusions on the lining of the respiratory tract. And they also help to trap microbes and debris. And when we're sick, we can help to expel them through the ciliary action. They're constantly beating in this sort of an upward motion. And then in addition to that, when we cough, we expel these tiny microbes and debris that are trapped in the mucus secretions of our respiratory tract. Excuse me as I cough. Also, then in our stomach, the very strong hydrochloric acid in our stomach, along with digestive protein enzymes, act as a barrier to help destroy any bacteria that is carried into our body, together with various foods that we ingest. And so really there's all these defenses in place to act as our first line to keep these pathogens at bay. But if a microbe does manage to make it past our first line of defense, then there's a secondary line of defense that comes into action to deal with that pathogen. This second line of defense is also called the non-specific immune response. And by non-specific, we mean that it will respond to any and all forms of pathogens that it detects, and it responds to all of them in very much the same way. So cells from our immune system that are constantly traveling through our body and patrolling our various tissues, searching for foreign material that shouldn't be present, if they come across foreign material and detect these foreign material, then white blood cells called leukocytes begin by attacking and engulfing these pathogens. Engulfing means surrounding them and almost eating them up in a way, internalizing them. It also, our immune system also sends out a signal which causes an inflammatory response. And an inflammatory response takes place where there is a increased blood flow to that site of the attack, and there is increased swelling, redness, heat, and also pain at this site. But what it does, it also allows white blood cells to arrive at the site more quickly by increasing the blood flow to that site. Next, these white blood cells, after these white blood cells arrive, another group of white blood cells called monocytes come into play. And a number of these will work together and join together to form larger macrophages. And the name macro, as you can imagine, indicates to us that it's quite a large type of cell. And this will also do the job of engulfing the pathogens. And after doing so, it will release enzymes to help destroy other pathogens that are still lingering around. Yet further, another type of white blood cells, as you get, there's many types of blood cells. There's monocytes, there's neutrophils, and neutrophils ensure that really everything gets destroyed. They engulf the pathogen and then they also release enzymes that will destroy all of these pathogens. And what is left then after these white blood cells engulf, deal, and neutralize these pathogens, what is left behind is fragments of proteins, dead white blood cells, and also dead pathogens. And all together, these form what we sometimes see at an infectious site, which is the pus that is formed in that site. So the pus that you see is all the remainders of the various cells and broken up proteins and dead white blood cells, dead pathogens, and all together forming this pus. And if at this point still this pathogen, that has placed our body under attack, is still not completely eliminated, then what comes into play is a third line of defense. And I guess I should talk about this diagram here quickly. This is what we just talked about, the non-specific immune response, where in this first panel, you can see that maybe a splinter or some sort of something pokes into your skin, breaks through your skin, breaks through that first line of defense, and together brings along with it some sort of a pathogen, some sort of a bacteria maybe. And by doing this, at this first sign of injury, these chemical signals are released. And together, other chemicals such as histamines and prostaglandins get released by the body's various cells and start out that inflammatory response. And these chemicals that are released cause the capillaries in that area to dilate, which results in an increase in blood flow to that area. Here you can see these capillaries have become a bit more wider. There's more cells flowing through them. And also they increase the permeability of these capillaries, allowing these white blood cells to permeate through the lining of this capillary and go to the site of that injury where those pathogens have gained entrance. And what they do then is these white blood cells engulf and eat up and digest these pathogens, these bacteria in this case probably, and various cellular debris, which then helps to promote the healing of that tissue in that area. So that was our non-specific, our secondary line of defense. And in the case where that hasn't completely worked and there is still some pathogens left behind, then our third line of defense comes into action. And this third line of defense usually is called into action when, excuse me, bacterial infections run out of control and become system-wide, or a virus runs out of control, destroying its target cells as it's trying to replicate into more virus particles. In this case, you have a response that becomes more specific to the type of pathogen that is in question. And it targets more what that pathogen is and how it's responding. So lymphocytes are very specialized white blood cells that are responsible for our body's more specific immune response, this targeted response. And so to help to slow down the invasion of these pathogens, neutrophils and macrophages are released, and they in turn then will release a chemical that will travel through the bloodstream and arrive at the hypothalamus. And at the hypothalamus, if you recall from our previous lesson, on the nervous system, The hypothalamus is very much in charge of controlling our body's temperatures. And so these chemicals, these signals at the hypothalamus start to reset the body's internal thermostat to be at a higher temperature, sometimes around 40 degrees Celsius. And this increased temperature then will make it difficult for bacteria to survive. And it gives our body's defenses a chance and more time to get to work. And this is exactly what we experience in the form of a fever sometimes when we're sick. In reality, so what we do is a fever makes us feel quite uncomfortable, and we sometimes take medications such as acetaminophen or ibuprofen to help us reduce a fever in order to feel more comfortable. But in reality, the very action of trying to reduce a fever sometimes might prolong an infection. However, not to say that you should let a fever run rampant, because if a body's temperature rises above 40 degrees Celsius, then it can be quite detrimental, and there can be quite extensive cell death, especially if it starts to really hit above 43 degrees Celsius. So it's really recommended not to interfere with a fever until around 40 degrees Celsius. But as it starts to go beyond that, it is recommended to take these fever reducing medications such as acetaminophen or ibuprofen to help to reduce the temperature so that you don't start to actually kill your own cells and get yourself even more sick. But every type of bacteria or virus particle that we can think of has these various proteins inside it, has characteristic proteins inside it, and also attached to its surface. And once it's attached to its surface, this displayed proteins on the surface can be used to identify it and to differentiate it from other cell types. And what we term these proteins that are displayed on the surface of bacteria or viruses, we call them antigens. And let me see if I have a figure here with antigens. So yeah, here we see that on our body cell, we have antigens, and these are our own antigens, and they're very similar. And on a invading cell, a pathogen, there might be distinctive antigens, such as these cone-shaped ones that may then be recognized as being different. So these proteins are called antigens. T cells are another group of cells from our immune system. These are produced by our bone marrow and are stored in our thymus gland. And they're able to really seek and identify these foreign intruders through their antigens. And once they recognize them, they signal for an attack. And they signal for the arrival of macrophages, which once they arrive, they will start to engulf whatever pathogen is present and recognized. And the antigens on the surface of the invader of that pathogen, once these macrophages engulf and in a way eat up these pathogens, what they do then is they take the antigens of the invader and they push it onto their own cell surface and display them on their own cell surface. And then you have these helper T cells that come along and copy the shape of these foreign antigens and release a chemical messenger called a lymphokine, which causes B cells in the body to start to divide rapidly. These helper T cells then will take that information about those foreign antigens and take them to the B cells so that the B cells can mass produce specific antibodies to these antigens. And antibodies, as you may know, are here we can look at them here. Here is, for example, an example of an antibody. Antibody are these molecules that are these Y-shaped molecules that are designed to fit over and recognize certain antigen markers. So for example, this invading microbe is displaying this type of antigen. Let's imagine that the shape of this antigen is this lollipop shape over here. And so each antibody that's produced specifically for that antigen will specifically fit and bind to that shape, that particular antigen that is on that particular invader. So, so as this attack on the pathogen continues by our immune system, killer T cells are activated to help to destroy the pathogen. So really you can see that there is a multi-pronged approach, and there are many levels of various cells that are brought into play. And this is really an orchestrated attack on this pathogen. So these killer T cells, they are very generalized in their attack. They release enzymes that will destroy not just the pathogen, but will even destroy our own body's own cells as well. So when you're sick with a cold or flu, and you start to experience that your throat is feeling sore and raw, that is exactly what you're feeling. You're feeling the action of the killer T cells that are in the process of destroying the virus, but also as they are doing so, they are also destroying your epithelial cells that are lining your throat. And those are the cells that the viruses like to target and invade. So as these viruses are destroyed, these epithelial cells that line the mucus lining of your throat are also destroyed. And that's when you feel that sore and rawness is through the action of these killer T cells that have got this very broad attack. So this type of defense by these killer T cells and the macrophages will just go on until antibodies are produced and antibodies arrive at the scene. So as it comes, this battle between the pathogen and our white blood cells really comes down to numbers. It becomes a numbers game. So in this form of immune response, it takes time to develop, which gives that pathogen sometimes more time and the opportunity to multiply itself and grow even bigger in numbers. But by the time that immune system initiates and comes to this form of the attack, when it comes to this point, at this point, you have sometimes millions upon millions of pathogens present by the time things have progressed this far. So here, the macrophages and the killer T cells are really doing their best to try and eliminate the pathogens. But at this point, oftentimes they might be quite outnumbered by the millions and millions that pathogens that have multiplied at this point. So even as they are destroying these pathogens and more of these macrophages and T cells are coming into action, even more pathogens are multiplying and being created. And at this point, it is really time for the antibodies to come and help out and to really help to give support to the macrophages and the T cells that are taking care of the killing of the pathogens. So once the antibody arrives and the antibodies are made, they have the very specifically shaped Y-shaped structure over here. And this Y-shaped structure fits over the shape of the antigen on the surface of the pathogen. And by doing so, it really neutralizes the pathogen and stops it from multiplying further or invading more cell. And this helps to stabilize the number of pathogen particles and stops them from further multiplying, and gives time for the macrophages and the other T cells, and gives them the time that they need to destroy the pathogens that they encounter, the pathogens that are still present. So finally, when you arrive at a point where the battle is finally looking like it might be won, and most of the pathogens are being eliminated and are eliminated, you have the action of suppressor T cells that will signal the immune system to stop and terminate that immune response. And at this point, most of the antibodies and the T cells will start to die off, but some will remain behind to help to guard that site, to ensure that really the battle is truly over. And these macrophages that remain, some that will remain, will continue to go on and clean up that site until, in fact, all the pathogens are eliminated. Memory B cells are do the job of carrying with them an imprint of that foreign antigen. So they will carry on and they will survive and they will continue to circulate through our body, and carrying an imprint of that foreign antigen with them, carrying the memory of that foreign antigen. And if the pathogen, that same pathogen ever, or one that carries an antigen on it similar enough for these memory B cells to recognize, if that pathogen or something very similar to it then ever enters the system again, those memory B cells will quickly be able to identify it and get it destroyed before it can actually establish itself in the body and start multiplying itself into millions and millions more. And this gives that individual these memory B cells that carry with them the memory of that foreign antigen. This is what gives that individual a certain immunity to that pathogen or to that invader. So here in our diagram over here, this diagram represents the specific immune response. And we can discuss it as we start over here. We can, everything that we talked about, we can talk about it as we follow this diagram along. So here you have an invading pathogen, in this case, maybe a bacteria. And as we said, all of these cells carry with them antigen markers on top that allows them to be identified. So here, this bacterium somehow gains entry into our body. And when it does so, it is these macrophages that are released by the immune system. These macrophages will come along and engulf this bacterium. And as they engulf and break down the bacterium, they will take those surface antigens from the bacterium and they will push it onto their outer membrane and display it on their outer membrane. And by doing so, they go and almost teach these helper T cells to identify these antigens that are present on the cell membrane of these macrophages. And then these helper T cells will go and help to identify these antigens that are further produced on B cells that will be displaying also antibodies in response to these specific antigens, and begins to produce even more antibodies. And the B cells produce lots more antibodies and release all of these antibodies, and they start to, these antibodies are very specific to the antigens on the bacterium, and they attach themselves to the antigens on the bacterium and really mark them for destruction and prevent them from further multiplying. So really there are 3 videos, and they are from one of the series that we've already been watching many videos from. That's the Crash Course series. And if we have time, we can watch these videos together at the end, and we can refresh our mind there. And then, yeah, I think each one of these is about 10 minutes long, so I'm just going to save them for the end of our lesson. So now let's discuss and distinguish between active immunity and passive immunity. So when you have immunity because of an immune response, this is called active immunity. This is where the body is on guard against that particular pathogen, and it will not be given the chance to cause any further problems, because now you have active immunity towards that pathogen. You have those memory cells, you have the proper antigens that are present on those memory B cells, and they're being able to be recognized, and you already have a certain amount of antibodies that are present towards them. But if that pathogen then ever enters again, and at this point, because we have that immunity already established towards it, we will not be very much aware that this pathogen has entered our body again, because it is found and destroyed before it causes any damage and really gets a strong foothold. That is where you have active immunity. Passive immunity gets acquired when you have antibodies that are given directly to the body. And this type transfer happens, for example, when between mother and baby through the placenta. And this is a passive immunity. So the baby gains the benefits of the antibodies that are produced by the mother, and they get passed through the placenta and will also circulate in the baby, and the baby will have this type of passive immunity to that type of pathogen. And also, some antibodies are also passed on in breast milk, and that's why it's very important for infants to be breastfed by their mother, so that they can take advantage of the passive immunity that can be passed to the baby from the mother. But this type of immunity only lasts for a short period of time. It's not a long-lived type of immunity. So in order to have a type of immunity that will last for a longer period of time, that's where vaccinations come into place. So vaccinations, or immunization is another name, is a way of creating active immunity, as we discussed, without having to actually be exposed to that pathogen and have to get sick from the full effects of that pathogen. So vaccinations work in this way, by giving you a chance to be exposed without being exposed to the entire live pathogen. And this really was something that began in ancient China, where the practice of having small bits of smallpox diseased skin were actually inhaled or sniffed up by healthy people to allow them to have to gain some active immunity to smallpox. In Western culture, Edward Jenner was the first to develop the first vaccine against smallpox, and he made use of a similar disease to smallpox, which was called cowpox, which also activated the immune system to produce antibodies against both cowpox and also smallpox. There was enough similarity. And since then, really, there's been many other vaccines, as you know, that have been produced. And Louis Pasteur, who invented the technique of pasteurization, which is used today for milk to reduce the amount of bacteria and microbes in milk, he also invented the vaccine for rabies. And in this case, there's no virus that is closely related to rabies. So that same method that Edward Jenner used by using cowpox to activate the immune system against smallpox, Louis Pasteur couldn't find such a similar virus to that. So instead, he had to use a different method. So by just trial and error, Louis Pasteur managed to find a way of weakening the rabies virus so that it could be injected without causing the rabies disease. But even though it was weakened, still antibodies could still be made, and the body could still have an immune response ready and present to that type of virus. So here we've talked about two ways. One is using a similar disease. So this is the example of cowpox being used to immunize against smallpox, and that was Edward Jenner's method. And then there was Louis Pasteur, who used the technique of weakening that virus so that it doesn't actually cause disease, but yet it does initiate an antibody response. And then in the mid-20th century, Jonas Salk used formaldehyde, and he used it to inactivate the polio virus and created a stable and usable polio vaccine. So they used some various different methods, but the ultimate goal of this vaccination is to give the body a chance to encounter the antigens present on the pathogen without actually having to get sick by an active pathogen. So the pathogen is either weakened or inactivated, or it's not the pathogen that is used, it's just something very similar to it, which is weaker, that is used. So today, vaccines are developed in somewhat the same manner as the earlier vaccines, using the same idea. Some form of the virus, usually a dead form or a weakened form of the virus, or sometimes even a piece of the virus, a part of the virus, is used to activate the immune response into creating antibodies and to prevent the disease from invading the system the next time that disease gets encountered by your body, so that you can remain quite unaware because you have immunity, and as soon as that virus or pathogen is encountered by your body immediately starts dealing with it before it really gets a stronghold, gets a foothold in there, and starts to make you sick. So immunizations now today are routine, and to a certain extent, for certain ones, are required by law. And those more traditional vaccines are ones that immunize against diseases such as diphtheria and tetanus and polio and pertussis, measles, mumps, and rubella. But more recently, we have vaccines against chickenpox. I mean, when I was a kid, there was no vaccine against chickenpox. You simply caught chickenpox and suffered. But I mean, today everybody gets a chickenpox vaccine. There's hepatitis vaccines, and there's definitely certain forms of pneumonia that you can be vaccinated against, and meningitis. These have all been added to the list of vaccines that are very typically available and recommended and given to most people nowadays in their childhood. So really, by using this attribute of our immune system and vaccinating, we have really managed to save countless lives. In fact, smallpox, the original virus that led to the first vaccine, this virus has been eradicated from Earth, and we only have samples of this virus only present in at the CDC, the Center for Disease Control in Atlanta, which and also some apparently some government research facility in Russia. So really, we've managed to eradicate a lot of these diseases through mass immunization. But sometimes you can have malfunctions of our immune system. As powerful of a defense system as it is, it can malfunction. It is vital to the body's defense mechanism against pathogens so that the body can carry out its normal functioning, but sometimes that immune system can malfunction and prevent the body from detecting pathogens and carrying on normally with its function. An example of a malfunction of the immune system, one of them is allergies. And what an allergy is an exaggerated response of our immune system to a harmless material. For some reason, our system will respond as if a foreign pathogen has entered the body. And there can be two types of these allergic reactions. There can be an immediate or a delayed. The immediate allergic reaction is really the most common and usually occurs within seconds of exposure to the allergen. When this happens, you have specialized antibodies that come along and trigger the release of histamines. And histamines increase the permeability of blood vessels, and this causes that area to become red and swollen, and also causes the release of cellular fluid to that area, resulting in watery eyes and runny nose. Sometimes you can have food allergies that can trigger even vomiting or cramps and diarrhea. And sometimes you can alleviate these types of symptoms with through the use of antihistamines. Asthma is another example. Asthma is the most common chronic disease that we have in North American children, and it causes problems when allergens are inhaled. And as a result of the inhalation of the allergen, it again triggers the release of the histamines that causes those passages in the lungs of somebody who has asthma to spasm and constrict, and making it very difficult to breathe. So these are examples of very immediate allergic reactions. But the delayed allergic reaction is initiated by those T cells, which have then become sensitized to a particular allergen because they have encountered this allergen previously. And this type of reaction, this delayed allergic reaction, occurs more slowly, but it also lasts longer. And food allergies are something that is becoming a big concern. And it's not entirely clear as to whether the cause is due to more food additives, or if there are environmental factors at play, or how is that creating a certain amount of sensitivity. But there has been a marked increase in the number of children who suffer from peanut allergies, for example, as these types of allergies continue to rise. Sometimes these food allergies can be quite severe, and when they are severe, they are known as anaphylaxis. And people can die from anaphylaxis if they don't get treatment right away. So once these antigens are present in our system and are circulating, those antigens will trigger the massive release of histamines. And this massive release of histamine causes a major dilation in the blood vessels throughout our cardiovascular system. And as histamine's job is to make these membranes more permeable, so this results in the leakage of fluids and proteins out of the capillary. And this leaking out of proteins and fluids, this will cause a very rapid drop in blood pressure. If you can imagine, if our cardiovascular system is suddenly more permeable and we're losing some fluid out of it very quickly, our blood pressure will tend to drop, and we will have reduced blood flow to our organs and tissues through our body. And at this point, in anaphylaxis, really emergency treatment is required that involves the use of epinephrine. And if you remember what epinephrine does, epinephrine increases the heart rate and leads to stronger heart contractions. So today, people who have severe allergies that might cause anaphylaxis tend to carry around with them an EpiPen, which is a dose of epinephrine that can be used to administer as soon as there is a massive allergy attack as it starts to happen. And currently, Health Canada has identified a list of 9 of Canada's top food allergens. The first one, of course, being the peanut. Number 2 is various tree nuts, such as almonds and walnuts. And number 3 is sesame seeds are an allergen. Milk. Many people are allergic to milk and the lactose in milk sometimes. Eggs. There's egg allergies. Many seafood allergies, both to fish and crustaceans, and especially shellfish. Soy allergies, wheat allergies, and allergies to sulfites, which are a type of food additive. And finally, another set of disorders associated with our immune system are autoimmune diseases. And here, the immune system fails to recognize itself and differentiate itself from what is foreign. And by this, it means that the system, for whatever reason, the reason isn't always known, sees the body's own cells as being foreign and starts to attack them. And it is that destruction of these cells, of our own cells, that then triggers the symptoms of that disease. there's some theories out there that suggest that all systems carry these renegade T cells and B cells that are capable of attacking the body, but they are suppressed through the action of these suppressor T cells that keep them in check. And then this theory suggests that the problem comes along when those suppressor T cells are weakened or their numbers decline. And rheumatoid arthritis is an example of this, when you have the immune response is mounted against the bones and the connective tissues of joints. Type 1 diabetes is another type of autoimmune system that is caused by the attack on those insulin-producing cells in the pancreas. Lupus is yet another example, and lupus is caused by when the antigen-antibody complexes build up in the walls of blood vessels, in the walls of joints and kidneys and skin, and cause a problem. MS, multiple sclerosis, is another one, is a disease that is caused when those myelin sheaths around the nerve cells get destroyed. If you remember, we talked about the myelin sheath around the axons of nerve cells, and their job is to wrap around and form these sheaths around the cell that help to transmit the nerve signal much more rapidly. So in MS, these nerves get demyelinated. The myelin sheath around them gets destroyed, and this reduces and prevents that nerve signal from being sent, and eventually leads to the person with MS to be paralyzed. And so far, there are some immune suppressor drugs that have helped to reduce the severity of these types of attacks in autoimmune diseases. And that brings us to the end of our lesson on the immune system. It wasn't a very long lesson. It was quite short and brief. Everything, I only focused on sort of the key areas. We can get a more detailed picture. We can look at those YouTube videos that I shared with you, and those are very well animated and quite entertaining. I don't know if I'll use this time to play these 3 videos back to back. You are welcome to stay on and watch them with me. I encourage you to watch them with me now, or if you want, you can also watch them again at your own pace, at your own time. But let's take a look at these videos now together. Okay, so here we go again. You guys are familiar with this set of videos, the crash course. So let's this one's about 9 minutes long. I think they're all about that much.
You may not know it, but your body is engaged in a never-ending battle. You are literally covered in staph and strep and E. coli and all sorts of dubious characters that are intent on using you and your body's many resources to feed themselves, find shelter, and reproduce as much as they want. And hey, we all gotta make a living. But it is not your job to give these guys a free lunch. So your body has developed a 3-part policy toward these shady customers, and its enforcement is handled by your immune system. The immune system is different from all the other systems we've talked about this year in that it's not a specific tissue, organ, system kind of system. Instead, it involves a whole bunch of different tissue groups, organ systems, and specialized but widely distributed defense cells. Together, this league of extraordinary substances joins forces to perform all of the defense functions your body depends on to keep you alive in an incredibly germy world. And the first line of defense in this never-ending battle, that's your innate or non-specific defense system. Like your average frontline soldier, it's prepared to immediately engage with anyone suspicious, and it mostly includes stuff we were born with, like the external barricades of your skin and mucous membranes, and internal defenses like phagocytes, antimicrobial proteins, and other attack cells. But some enemies must be fought with special forces, and here your body can deploy your adaptive or specific defense system, which is more like your SEAL Team 6. It takes more time to call in, but it's specially designed to go after specific targets, and it keeps files on those bad guys so it knows how to handle them next time around. But today we're going to focus on your innate system and look at how it uses an arsenal of physical and chemical barriers, killer cells, and even fever to keep you healthy, proving that sometimes the symptoms we associate with illness are actually the signs that we're healing. Just because something is simple doesn't mean that it can't be elegant. I mean, your body is capable of some incredibly sophisticated things, including defending itself from infection. But occasionally, there's something to be said for brute force. And a lot of your innate immune system's functions aren't exactly subtle. For example, your body's very first line of defense is a simple physical barrier. And it works. Like a wall around a fortress, your skin does a fantastic job of keeping out all manner of malevolent microorganisms. As long as that tough, keratinized epithelial membrane doesn't get torn open or busted up too much, you could probably, make snowballs out of raw sewage and still be all right. Although, no. Your many mucous membranes also provide a handy physical barrier. You'll remember that they line any cavity that opens up into the germy outside world, including the respiratory, digestive, urinary, and reproductive tracts. Not only do your skin and mucosa supply simple physical protection, they also pack some serious chemical weaponry. Eat some questionable leftovers for lunch? Don't worry, your stomach is literally filled with acid, so you probably are covered. Walk face first into your coworker's nasty sneeze cloud? No worries, your nasal passages can whip up a tissue box worth of sticky mucus to help trap viruses before they enter your lungs. You've also got bacteria-fighting enzymes in your saliva and lacrimal eye fluid, and peptides called defensins in your skin and membranes that help keep bacteria and fungi from setting up shop around inflamed or scraped skin, which no matter how careful you are, you're gonna get one way or another. Maybe you shave with a dull blade, or you just brush your teeth too hard, and don't get me started about the dangers of bagel cutting. So when you've breached that first simple line of defense, it's time to call on your second line of internal innate defenses. This is where your body starts pulling strategic maneuvers like firing up a fever, releasing chemical signals, causing inflammation, or other defensive tactics that help identify and attack infectious invaders. Some of the first defensive cells on the scene are your phagocytes. Their name literally means to eat, and like Pac-Man, they indiscriminately chase down intruders and gobble them up. And they come in a few different varieties. First, you got neutrophils, which are the most abundant type of your white blood cells. They kind of self-destruct after devouring a pathogen, and in fact, you've probably seen piles of their little dead bodies, because that's what pus is made of. But the bigger, tougher phagocytes are the macrophages. They're derived from monocyte white blood cells that have moved out of the bloodstream to occupy tissues. And some are free types that patrol tissues looking for creepers, while others are fixed, attached to fibers in specific organs, devouring anything suspicious that passes by. So when a macrophage, in say the finger I just cut slicing a bagel, sees a new bacterium coming along, it snares it using cytoplasmic extensions, reels it in completely, engulfs it, and essentially digests it and spits the rest out. And unlike neutrophils, it can do this over and over again, like a boss. So not all your defense cells are phagocytic. You've also got cells with what is by far the awesomest name of any cell in the body, the natural killer cells. You can call them NK cells if you want to, but why would you do that? Anyway, these tiny assassins patrol your blood and lymph looking for abnormal cells and are unique in that they can kill your own cells if they are infected with viruses or have become cancerous. How can they tell? A normal, healthy human cell contains a special protein on its surface called MHC1, or major histocompatibility complex. But if it's infected, it stops making that protein. And if an NK cell detects a defective cell, it doesn't swallow it whole like a macrophage. It pokes it with an enzyme that triggers apoptosis, or programmed cell death. Pretty awesome. So those are some ways your innate immune cells handle their enemies, but how do they know where to look in the first place? So let's talk strategery. So say you're in a banana factory and you slip on a banana peel and you scrape your knees. Your outer fortress has been breached and the pathogens are just flooding in like orcs through Helm's Deep. Banana factories are very dirty places. Now your body wants to contain the spread of pathogens, clean up the mess, and get healing as quickly as possible. So it cues up your inflammatory response. This is basically an internal fire alarm, only it uses chemicals instead of cytokines sirens to get the message across, and instead of smoke and fire, you sense redness, swelling, heat, and pain. For example, in the event of injury, specialized mast cells in your connective tissue send out histamine molecules, and histamine is great at calling in the cavalry. For one thing, it causes vasodilation, which creates redness and heat, exciting injury. Now, those things might freak you out a little, but they're actually signs of healing. The increased temperature, for example, ratchets up the cell's metabolic rate so they can repair themselves faster. Meanwhile, histamines and other inflammatory chemicals also increase the permeability of blood vessels, causing nearby capillaries to release protein-rich fluids. This causes swelling, which again is actually a good thing because that leaked protein helps clot blood and form scabs, while the lymphatic system sucks up and filters that extra fluid, cleaning it up before putting it back into your bloodstream. And of course, like chum to sharks, an inflamed knee is also going to attract a bunch of local phagocytes, which find it easier to escape your now leaky capillaries, and lymphocytes that are also flowing freely, helping to destroy pathogens while also cleaning up dead cell wreckage. And don't forget, during all of this, the neutrophils have been doing their best, but they were the first wave to arrive, so by this time, they're starting to die in heaps. They're triggered when the injured knee skin cells release chemicals that begin leukocytosis, the release of neutrophils from the bone marrow, where they're made, into the bloodstream. To attract the neutrophils to the damaged area, inflamed endothelial cells in the capillaries send out chemicals that act like homing devices. And when the neutrophils arrive, they cling to the capillary walls near the injury, flatten themselves out, and squeeze through the vessel walls to get to work. Your big monocytes eventually roll up to the battle and transform into hungry macrophages, replacing the first line of now dead neutrophils and basically just eating up any lingering enemies and then cleaning up the carnage. All this works pretty well in most circumstances, but you may have noticed with a more major injury or an especially nasty virus or infection, sometimes your local troops get overrun. When white blood cells and macrophages run into more foreign invaders than they can handle, they let loose pyrogen chemicals that tap the hypothalamus and raise your body's thermostat, calling in a systemic fever to burn everything. The resulting temperature rise increases the metabolism of your cells so they can heal faster, and it also tells the liver and spleen to hold on to all of their iron and zinc so those things can't contribute to bacterial growth. But even then, sometimes you find yourself facing a more formidable foe. That's when you call in the specialists, your adaptive immune defenses. And to learn exactly how they save the day, have to watch next time. But for now, you learn that your immune system's responses begin with physical barriers like skin and mucous membranes, and when they're not enough, there are your phagocytes, the neutrophils and macrophages. You also learn about natural killer cells and the inflammatory response, and watch as all of these elements save the day when you slipped on a banana peel. Thank you to our headmaster of learning, Linnea.
So now we will move right on into part 2.
What's true in World of Warcraft is also true in your immune system. To defeat your enemy, you have to know your enemy. Uncover its weaknesses. Learn how to see it before it sees you. We've already talked about how your innate defense system keeps out or quietly neutralizes pathogens without too much fuss. But sooner or later, a threat's going to come along that's stronger than what the first responders can handle. That's when it's time for the adaptive or acquired immune system to step in. While your innate system takes its zero tolerance policy very seriously and tries to toast any foreign microbe that it encounters, your adaptive system does things differently. It has to be expressly introduced to a specific pathogen and recognize it as a threat before it will attack. As its name suggests, you're not born with a working adaptive immune system. It's slow to act, in part because it takes time for it to shake hands with so many pathogens and get to know them. These introductions may be organic, like touching a dirty faucet in the bathroom or walking into a sneeze cloud, or they may be premeditated, which is why vaccination is pretty much the greatest thing to happen to medicine ever. But once it's been introduced to a potential threat, your adaptive defenses never forget it. And this ability to remember specific pathogens is one of the key differences between the adaptive and innate defenses. Another main difference is that adaptive immunity is systemic. Rather than being restricted to a particular infection in, say, a sinus or a sliced finger, your adaptive system can fight throughout your whole body at once. And it does this by deploying one or both of its separate but cooperating defenses, your humoral immunity and your cellular defenses. Your humoral immunity, which you might not have heard of before, works by dispatching important proteins that I'm sure you have heard of. Antibodies. They're made by special white blood cells, and they patrol the body's humors, or fluids like blood and lymph, where they combat viruses and bacteria moving around the interstitial space between your cells. Much of what you know or have heard about or think of when your immune system comes up actually has to do with your humoral immunity. It's why if you had mumps as a kid, you probably don't have to worry about getting it again for the rest of your life. It's also why doctors and nurses and patients who have been infected with the Ebola virus, a disease once thought to be incurable, have lived to tell about it. And it's why vaccinations work. Whether you're protecting yourself from infections or playing an MMO, one of the first steps in any good defensive strategy is to be able to tell your friend from your foe. And in the case of your immune system, that means being able to identify antigens. An antigen could be an invader from the outside world, like a bacterium, virus, or fungus, or it could be a toxin or a diseased cell within your own body. But in any case, antigens are large signaling molecules not normally found in the body, and they act as flags that get the adaptive immune system riled up. So let's say a flu virus gets inside of you, and it's floating around trying to find a good host cell to start multiplying inside of. So before it finds that cell, hopefully it will be paid a visit by one of the stars of your humoral response, a B lymphocyte. Like all blood cells, these guys originate in your bone marrow, but unlike other white blood cells, they also mature in the bone marrow too. And as a B cell matures, it develops the ability to determine friend from foe, developing both immunocompetence, or how to recognize and bind to a particular antigen, as well as self-tolerance, or knowing how to not attack your body's own cells. Once it's fully mature, a B lymphocyte displays at least 10,000 special protein receptors on its surface. These are its membrane-bound antibodies. All B lymphocytes have them, but the cool thing is every individual lymphocyte has its own unique antibodies, each of which is ready to identify and bind to a particular kind of antigen. That means that with all of your B lymphocytes together, it's like having 2 billion keys on your immune system's keychain, each of which can only open one door. So part of your immune system's strategy is just to win with overwhelming odds. The more unique antibodies your lymphocytes have, the more likely it is that one will eventually find, bind to, and mark a particular antigen. Once they've matured, B cells colonize or seed your secondary lymphoid organs like your lymph nodes and start roaming around in your blood and lymph. At this point, they're still naive and untested, and they won't be truly activated until they meet their perfect enemy match. Which brings us back to the flu virus. When the right B cell finally bumps into an antigen it has antibodies for, usually in a lymph node or in the spleen, and recognizes it, it binds to it. This summons the full power of the humoral immune response, and the cell basically goes into berserker mode. Once activated, the B cell starts cloning itself like crazy, quickly producing an army of similar cells, all with the instructions for the exact same antibodies that are designed to fight that one particular antigen. Most of these clones become active fighters or effector cells, but a few become long-lived memory cells that preserve the genetic code for that specific successful antibody. This ensures that if and when the antigen returns, there will be a prepared secondary immune response that's both stronger and faster than the first. This is key to why vaccinations are so brilliant and important, which I'll come back to in a minute. But while the memory cells are just there to hang back and record things, the effector, or plasma cells, are packed with extra amounts of rough endoplasmic reticulum, which acts as an antibody factory. These cells can mass produce the same antibodies over and over for that particular invader, spitting them out into the humor at a rate of around 2,000 antibodies per second for 4 or 5 days until they die. And the antibodies they make work the same way that the membrane-bound ones do. They're just free-floating. So they ride the tides of blood and lymph, binding to all the antigens they can find and marking them for death. Now, antibodies can't really do the killing themselves, but they do have a few moves that could make it hard for intruders to take hold. One of their most effective and common strategies is neutralization, where antibodies physically block the binding sites on viruses or bacterial toxins so they can't hook up to your tissues. And because antibodies have more than one binding site, they can bind to multiple antigens at the same time in a process called agglutination. The resulting clumps can't get around easily, which makes it easier for macrophages to come and gobble them up. And not only that, but while all this is going on, antibodies are also ringing a chemical dinner bell, calling in phagocytes from the innate immune system and special lymphocytes from the adaptive system to destroy these messy little antigen antibody clumps. So the point of all of this in the short term is to keep you healthy, but in the long term, this process also adds to your overall immunity. The humoral response allows your body to achieve immunity by encountering pathogens either randomly or on purpose. Active humoral immunity is what we were just talking about. It's when B cells bump into antigens and start cranking out antibodies. This can occur naturally, like when you catch the flu or get chicken pox or pick up some nasty bacterial infection, or it can happen artificially, particularly through vaccination. Most vaccines are made of a dead or extremely weakened pathogen, and they work on the premise that because the secondary immune response is more intense than a primary response, by introducing a pathogen into your body, you're priming it to fight hard and fast should that antigen show up again. In the case of typically non-fatal infections like the common flu, this immunity should at least spare you from some of the most severe symptoms. But in the case of more serious diseases like polio, smallpox, measles, and whooping cough, vaccinations can be truly life-saving. Now, some antigens, like those for mumps or measles, don't really change much over time, so a few immunizations will leave you set for life. But others, like influenza, are constantly evolving and changing their surface antigens, so immunity to last year's flu probably doesn't work against this year's flu. Still, acquired immunity doesn't have to be active. Babies, for example, naturally obtain passive humoral immunity while still in the womb. They receive ready-made antibodies from their mothers through the placenta and later on through breast milk. And that works pretty well for a few months, but the protection is temporary because passively obtained antibodies don't live long in their new body, and they can't produce effector cells or memory cells, so a baby's own system won't remember an antigen if it gets infected again. You can also acquire this kind of temporary passive immunity artificially by receiving exogenous antibodies from the plasma of an immune donor. This is what recently saved some doctors and nurses who had contracted the Ebola virus from infected patients. A serum was made from the blood plasma of other medical workers who had been infected and survived. The antibodies help defend the patients from the virus before their own active immunity could identify that particular antigen and start creating their own antibodies. It's not the same as a vaccine, which immediately engages your B cells, but it can buy a patient some crucial, life-saving time against an infection that would otherwise quickly kill. But B cells and antibodies are only part of the immunity equation. There are plenty of pathogens that quickly worm their way right inside your cells, where they're safer from the humoral response and free to multiply as much as they'd like. Luckily, your immune system has yet another game plan and a new set of players ready to fight that final battle with cell-to-cell combat. Make sure you catch our final episode next week and learn all about this epic battle royale. But as for today, in our second to last episode, you learned how the adaptive immune system's humoral response guards your extracellular terrain against pathogens. We looked at how B cells mature, identify antigens, make antibodies, and how antibodies swarm pathogens and mark them for death. We also talked about active and passive humoral immunity and how vaccines work. Thank you to our headmaster of learning, Linnea Voyev, and thank you to all of our Patreon patrons.
Okay, so now part 3.
It is time. We have arrived at the final conflict, the Battle Royale. A fight to the, well, hopefully not death, but a big fight anyway. It only seems fitting that we spend this, our last episode of Anatomy and Physiology, talking about one of your body's last-ditch efforts to defend itself at all costs. This is what happens when all the other fail-safes have failed. Your skin and mucous membranes did what they could as physical barriers against infection, and your humoral immune response cranked out antibodies in an effort to keep your interstitial spaces healthy. But when those systems weren't enough, your cells themselves were breached, and pathogens and abnormalities began to run amok where antibodies could not get to them. Now it becomes the business of your cell-mediated or cellular immune response. And that's where stuff gets real, where cell fights cell, and where heroes look like T lymphocytes. These lymphocytes, known on the streets as T cells, go after body cells that have been hijacked by things like viruses or bacteria or become cancerous. T cells cause inflammation, activate macrophages, get other T cells fired up, and generally regulate much of the immune response. Which is important because of all the ways in this course that we have described how you could die, two that we have neglected to mention are what happens if your body completely fails to protect itself, and what happens if your immune system goes rogue and attacks your own healthy cells. But even when they're functioning well, some of your immune cells are careening around your body like miniature biological versions of Mad Max war boys, amped up on signaling chemicals, scouring the terrain for hostiles, and covered from top to bottom in the dismembered parts of the enemies that they have vanquished. They're out to protect all of the tissues and organ systems that we've been talking about for the past 46 weeks, and these guys play for keeps. If there are cells in your body that look and act like they're from some post-apocalyptic hellscape, it's gotta be the cells in your immune system. Aside from the fact that they go around literally eating their enemies and have names like natural killers, some of these cells are dressed for the part too. Specifically, they go around wearing parts of the organisms they've killed so others can see them. Sounds a little bit messed up, but we're talking life and death here. The stakes are high, and this kind of behavior occurs both in your innate immune response and your acquired response. We've already talked about how in the innate response, when a phagocyte sees a suspicious character, it engulfs it and kills it, right? But what we didn't get into before is that during its attack, the phagocyte actually breaks the pathogen into tons of tiny molecules and then proudly displays those broken bits in grooved proteins on its outer membrane. These proteins are called major histocompatibility complexes, or MHCs, and they're a lot like how Vlad the Impaler decorated his front yard with the bodies of his skewered enemies, or how a battle-crazed warrior might show off a necklace made of knuckle bones. Because cells from both your innate and adaptive branches do this grisly accessorizing characterizing like it's their job, they are referred to as professional antigen-presenting cells. Which might make you think, is there an amateur version of an antigen-presenting cell? And yeah, there kind of is. Every nucleated cell in your body, which means all of your cells except for red blood cells, have one kind of MHC protein on their surface called class 1 MHC. MHC1 proteins present short chains of amino acids that are based on endogenous proteins, that is, proteins synthesized inside that cell. So if a particular cell is healthy, the antigens on its MHC1 tell roving immune cells that everything is okay inside, nothing to see here. But if the cell is, say, cancerous and it's making abnormal proteins, then it'll fix bits of those proteins to its MHC, which alerts immune cells that there's a problem inside and basically asks to be killed. Now, your immune-related cells, like macrophages, dendritic cells, and B cells, wear class 2 MHC proteins on their outsides. These are the professionals. Class 2 MHC proteins bind to fragments of exogenous antigens, like a virus that's been engulfed, broken up, and displayed to get the attention of other cells. And this is how MHCs are totally essential for the cellular immune response. Because the heroes of your cellular defenses, the T cells, can't actually detect whole antigens. They can only recognize them when they're all diced up and decorating an antigen-presenting cell. T cells are made in the bone marrow, but they mature in the thymus, the lymphoid gland that sits on top of your heart, and which is actually what the T in T cell stands for. And you have several different kinds of T cells, but the two you really have to know about are helper Ts and cytotoxic cells. Helper Ts themselves can't kill, but they can activate cells that do, and they help call the shot for the whole adaptive immune response. Meanwhile, cytotoxic cells are the ones that actually do the killing if the cell's gone bad. Now, much like how a naive B cell carries antibodies for one specific antigen, a naive helper T cell has receptors that will only bind to one specific combination of a class 2 MHC and a particular antigen. If that match is right, the helper T bonds to the MHC antigen bit and it gets activated. Then, just like with the B cells we talked about last time, the helper T starts copying itself like crazy, making a few memory T cells as well, which remember that particular antigen should it meet one again in the future. And it also produces a whole mess of effector T cells, mostly more helper Ts, but also some regulatory T cells that I will get to in a minute. But the main thing the helper T cells do is raise the alarm that tells other immune cells that there is a problem. And they do this by releasing a cocktail of chemical messengers called cytokines. When a cytokine enters another helper T, that cell usually starts dividing, making more memory T cells and more helper Ts, which release more cytokines that keep boosting the signal. And some of those cytokines also go on to help activate the cytotoxic T cells. You know that macrophages from the innate system just sort of roll up and swallow pathogens whole, but cytotoxic T cells do their killing a little differently. They roam the blood and lymph looking for hijacked amateur body cells that are asking to be killed. Basically, these infected cells are already dying, so they've digested some of their invaders' proteins and stuck them on some of their class 1 MHCs, effectively waving a surrender flag made of fragments of the very virus or cancer that is destroying them. If a cytotoxic T cell with the right receptor floats by, it binds to the antigen MHC combination and moves in for a mercy killing. It does this by releasing special enzymes that punch holes in the cell's membrane or otherwise trigger apoptosis, killing both the cell and whatever is inside of it. Then the cytotoxic cell just detaches and continues to run down other prey. So by now it should be pretty obvious that without T cells, there basically is no adaptive immune response, and it really all comes back to the helper Ts, which is why immunodeficiencies can be so deadly. AIDS, for example, is caused by the human immunodeficiency virus that specifically attacks helper T cells, and without the helper Ts, there wouldn't be much of a humoral response either, because the cytokines that come screaming out of the helpers not only activate other T cells, but they also finish the training of the B cells. The fact is, most of your so-called naive B cells don't get fully activated and become memory or effector cells when they first bind to an antigen. And there's a good reason for that. Since antibody receptors are generated randomly, you might wind up with B cells that could bind to your own healthy proteins, like, say, your growth hormone. So once a B cell interacts with a substance, whether it's growth hormone or some dangerous bacterium, it still needs to bind to it, engulf it, and present some fragments of it on its surface. But then it'll stop to await inspection. It pauses until the right helper T cell comes by to check out its presentation. If the T cell binds to the presented fragment, then it releases cytokines which fully activate the B cell, and suddenly you got antibodies going everywhere. But if it doesn't, then the B cell just goes about its business and doesn't trigger an immune response. This check and balance between Bs and Ts is an important safeguard against your immune system becoming too good at its job, which is a very real risk. A hyperactive immune system can cause mayhem by losing its ability to distinguish enemy from self. as it turns on your own body. Your regulatory T cells, another type of effector, help prevent this by releasing inhibiting cytokines that tell other immune cells to stand down once the initial threat has been handled. Without that regulation, the body might start cranking out too many antibodies and cytotoxic cells that could damage or destroy its own tissues. This dangerous confusion is what causes many autoimmune diseases, like multiple sclerosis, which eats away at the myelin sheaths around neurons, or type 1 diabetes, which tears up the pancreatic cells that make insulin. So the takeaway here is that your immune system is usually really good at its job, which is to kill stuff in the name of keeping you alive, and you really don't want it to go rogue on you. Because if there's one thing you should have learned in the past year with us, it's that your body is both resilient and fragile, and it survives only when the sum of its many complicated parts stays balanced and works together. And that is the glorious wonder of you. As we wrapped up our tour of the immune system today, you learned how the cellular immune response uses helper, cytotoxic, and regulatory T cells to attack body cells compromised by pathogens. We looked at how cytokines activate B and T cells, and what happens if your immune system goes rogue and starts causing autoimmune trouble. Thank you to our headmaster.
All right, guys, that is it for these 3 videos. We watched them together. Don't forget, we have our Unit 4 assignments due. Let me just okay. Here's our welcome document. So Unit 4 assignments are due this Sunday, November 20th. And, oh, I actually forgot we were supposed to look at some student presentations today. All right. Maybe we can do that. Maybe we can do that, start doing that on Monday, okay? So for those of you who were hoping to present today, we can maybe start doing that on Monday then. I think, yeah, we'll start doing that Monday and Wednesday. We'll start Monday and maybe it might spill over into Wednesday. Okay, so make sure you finish your unit assignments and hand them in by Sunday, November 20th. I have links to the Dropbox here. So just use the links to submit your assignments to the Dropbox on Sunday. And make sure that you label them with your name and indicate which unit it is, so that I can just download all the assignments in one shot and not have to worry about going and renaming the files with your names and putting your numbers on it. Please take care of doing this for me. And yeah, any of you who still have assignments that are outstanding and haven't done them, you need to get those in. If you are in that situation, hopefully you've talked to me or should be talking to me about what is your reason and what's happened. But if you don't hand in your assignment, unfortunately, you don't get any type of a mark for it. Okay. So yeah, this is where we are in our course. As you can see, we are down to our last unit, Unit 5. We will have these lessons. We have 4 more lessons left. So 2 more weeks. And then we will have a tutorial session on Monday, November the 5th. Sorry, Monday, December the 5th. That is a mistake. Monday, December the 5th, followed by our final exam on Wednesday, December the 7th. And at that point, we are done with this course. And everything that you're supposed to hand in, you should have handed in by Sunday, December 4th, or at the latest at the time of this exam. Yes, because I'm actually, I will be, I'm going away after we do our exam, so I won't be here to mark any further assignments that come in beyond this. Once we do our exam, I will mark it, I will return it to you, and then I won't be able to really do much after that. So please get all your assignments, everything in by December 4th, December 7th at the latest. Okay. If you have any problems or concerns, please reach out to me and discuss it. Otherwise, if there's no questions, I'll see you on Monday, where we will do lesson 17 and start our student presentations. Okay. All right, everybody. Have a good night.
Good night, Miss.
Bye.
Good night.
Very much.